So the next important mathematical modeling concept is mathematical modeling of thermal systems. Let us recall the definition of what is the capacitance and resistance for the thermal systems. And in mathematical modeling, every quantity will be expressed as either in terms of resistance or in terms of capacitance. Here, the resistance and capacitance are defined for a thermal systems, hence usually it will be called as thermal capacitance or thermal resistance. Let us define what is thermal capacitance. So the thermal capacitance is denoted by C. The thermal capacitance is defined as how much amount of heat will be stored per unit degree rise in temperature. So dQ by dt. dQ is nothing but it is the rate of heat flow. With respect to per unit degree rise in temperature. So we will call it as temperature differences. And also other thing is there, thermal resistance. Thermal resistance is denoted by R, and thermal resistance will be defined as it is the reverse of capacitance. It is how much temperature rise with respect to unit heat transfer flow. So this is the equation for thermal resistance. This is temperature difference, and this is rate of heat flow. So this is how we will be defining a thermal system. How to remember this? Sometimes we will be in confusion that dQ by dt is for C or dt by dQ is for C. So this confusion will be there. So in order to remember this, you remember Q is equal to mCp delta T. Q is equal to mCp delta T. It is a familiar heat transfer equation in thermal systems. So this Q, if I take with respect to mass flow rate, Q will be equal to Cp into delta T. So when I take with respect to time dQ, so it will be dQ into Cp into delta T. So what is Cp here? Cp is dQ by dt. So this is the equation we arrived at thermal capacitance. Capacity, how much it can store the heat. So capacitance means heat. Here, for ease of understanding, what we will do is this prefix is given C thermal and R thermal. This prefix can be used because we need to differentiate between thermal resistance, thermal capacitance, and hydraulic resistance and hydraulic capacitance, because of which this discrimination will be there. Let us solve one of the problem in thermal systems, that is temperature control system. This is also called as thermometer. So what they will ask in the exam is obtain a transfer function for thermometer system, obtain a transfer function for temperature control system. Like this they will ask a question, or else in the statement wise also they can ask a thermometer dipped in a vessel containing liquid at constant temperature constant temperature, they may mention whether it is a Ty or theta I. For ease of sake, we will use theta I of T. Theta I of T, which has a thermal capacitance C and thermal resistance R. Then if the temperature stored in thermometer is theta naught of T. So theta naught of T is the temperature stored in thermometer. Obtain transfer function of the system. So this is a general question they will ask for 10 marks. So here taking the data is very important. The question seems to be 4 lines, but the solution is very simple. What I will do is, first I will transform the data into an equation. First let us understand what is the given here. Earlier, here there is a thermometer. That thermometer is dipped in a vessel. So this is a vessel. This is vessel. This is thermometer. Thermometer dipped in a vessel containing a liquid. So this is a liquid. This is a liquid. So the temperature of the liquid is theta I of T, and the thermometer will be showing some temperature. This temperature is theta naught of T. So this is a question they have given. Theta I of T is the liquid temperature, theta naught of T is temperature in thermometer or a storage temperature. The understanding of this problem is very simple if you understand the law of conservation of energy. Energy can neither be created nor be destroyed, but only transform one form of energy to other form. Here you will be transforming the heat stored in the water to the heat stored in thermometer. In other words, the thermometer will be giving what is the temperature of water inside this vessel. That is a concept here. So I will try to write that in an equation. So heat transferred will be equal to heat received. So here heat absorbed or heat is receiving by thermometer. Heat absorbed by thermometer. So a small theory, just I will write what is the heat transferred here. So water will be absorbed by a thermometer. Heat transferred by the water will be equal to heat absorbed in the thermometer. So this line is important. What is the heat transferred in water? Again we will recall what is the definition of capacitance and resistance. So here what is capacitance? dq by dt. What is resistance? dt by dq. Here finally you have to know we are writing the equation for q. Here also we are writing equation for q. Again it is in steady state. It depends upon the time. What is dq here? C into dt, one equation, and another one is dq into r, that is dt by r, that is the other equation. Two equations you have to write. So what we will be doing is, here there will be a temperature transfer, there will be a heat transfer from liquid to thermometer. So there will be a transfer of heat. Whenever there is a transfer of heat, there is a resistance. So what is the heat transferred from the water will be inlet minus outlet temperature divided by resistance. What basically we have used here is dt by R, this equation. Just rearrange this. dq will go here, dt by R. This is a equation we are using here. And what is the heat transferred in thermometer? There is no transfer. It will receive the heat. It will store the heat. Here heat is stored. Whenever you have a word stored, capacitance will be coming into the picture. So here C, where C is the thermal capacitance, C into, it is again rearranging the word, dt, d theta naught divided by dt. Again I said these are the steady which depends upon the time. Theta naught by dt. After some time it will show the temperature and that will be constant. The theta naught is the, in the question, the temperature stored in thermometer. This is very important. And what is the temperature stored in water? It is theta I. And what is R and C? Capacitance and resistance. That's all, finished. Now what we have to do is we need to know which is the output and which is the input. Which is the output? The output is theta naught. Which is the input? Theta I. So we need to write the expression. Before that, I need to change differential equation to a Laplace domain. So apply Laplace transformation. If you apply Laplace transformation, theta I become theta I of s, there is a time, minus theta naught of s will be equal to, I will multiply R here, R C, d by dt is there, s into theta naught of s. Rearrange the terms, then theta naught of s divided by theta I of s will be equal to 1 divided by 1 plus RCS. This is an equation for the ratio of outlet and inlet temperature for a thermometer system or a temperature control system. This concept is very important. What we have basically done is we have correlated the equation of capacitance as well as resistance. Capacitance, where it is storing the heat, it is storing in thermometer. Resistance, where it is giving resistance, it is giving in vessel in between the water inside the vessel and thermometer. So heat is transferring from water to thermometer and heat is storing in the thermometer. So here there is a resistance, here there is a capacitance. Equate those two things, you will get the final thing. So this is the temperature control system. There is another thing, that is furnace system, or simply what we will call it as heating furnace system. Obtain a transfer function for furnace system. They can ask the question. Obtain a transfer function for heating furnace system. That is the simplest question they will ask. Let us try what is happening in the furnace. So this is a furnace. The furnace is having a heater coil. This is a coil. This is furnace. So inlet, there will be a water, theta I of t. So it is an inlet water and the water is being heated here. Water is being heated here. Then you will get outlet water, theta naught of t. Between this inlet and outlet there is a insulation. This insulation is adiabatic. Adiabatic means it is perfectly insulated so that the temperature is not being wasted inside the chamber. So if anything is there surroundings, it is theta. Since it is a adiabatic, we can neglect the value of theta. So this is how the furnace system will look. So mainly theta I of t be the inlet water temperature. After that it is heated in the heater. After that you will be getting the heated water. That heated water is theta naught of T. That is the temperature of heated water. Theta I of T is temperature of inlet water. Assume that it is a cold water heated up and we got hot water. That is the system what we are using here. So let us apply law of conservation of energy here. What is the total heat in the system? The total heat in the system will be equal to, this is a total heat in the system will be equal to the total heat in the system will be equal to how much amount of heat is utilized to heat up the water. So just I will write heater and surroundings. So how much heat utilized to heat the water, then what is the heat at surrounding? What is the heat at surrounding? So this is the law of conservation of energy equation. What is the heat utilized here? What is the heat utilized here? So again we will recall the thermal capacitance and thermal resistance. What is the heat at the water? The water is being heated up and yes, it is having capacitance. The capacitance will be there during heating of water. So that will be equal to C into how much you are heating? It is d theta naught by dt. So this is a heated temperature divided by time. And what is the heat transferred through the surroundings? What is the heat transferred to the surroundings? So surroundings means theta naught minus theta. If there is no insulation, theta naught minus theta. So theta naught minus theta divided by R. So this is the equation for heat flow. Again, I will apply Laplace transformation. What happens? Q will be changing to Q of S equal to Cs into theta naught of S plus theta naught of S minus theta of S divided by R. R is neglected. Why? Compared to outlet heat, this theta is very negligible. That's why you neglect. So rearrange this. Q of S will be equal to Cs into theta naught of S plus theta naught of S. R will go here. This is R and divided by R. So here theta naught of S is taken as common. Theta naught of S is taken as common. R Cs plus 1 divided by R. So rearrange this. What is the output? Output is theta naught of S. What is the input? Input is heat flux. Output is the hot water what we are getting. Hot water is temperature at hot water, theta naught. Input is furnace, heating the furnace, that is the input. So it will be equal to R divided by 1 plus R Cs. So this is the equation for furnace system or heating furnace system. So these two derivations will be asked. Even the simplest form is just you need to transform resistance and capacitance into the equations. That is very important in case of thermal systems. And just in the temperature or thermometer system, what we have done is we have done only two things. We have just substituted the value of resistance and capacitance. That's all. Here also we have done the same thing, only the change is equation. Here the temperatures are output and input. Here output is the temperature, input is the heat flow. That is very important. In other words, we will call it as heat flux. So here what we have done basically, thermometer is dipped in a vessel containing a liquid having a temperature theta 1, thermometer having a temperature theta naught. So what is the heat transfer here? Heat transfer by the water bath will be equal to heat transfer to the thermometer. Just substitute the value of Q, you will get the equation. Here also same thing, write the law of conservation of energy equation, substitute the value of heat transferred through the water and heat transferred through the surroundings, then substitute, then apply Laplace transformation, you will get the answer. This is about modeling of thermal systems. Thank you. The next important topic is actuator. What is the actuator? Actuator will be there after the microprocessor unit. What it will do? It will activate the systems. The output of the actuator will be either linear motion or rotary motion. Depending upon the actuation, how it is actuated, whether it is based on hydraulic pressure or whether it is based on pneumatic pressure. The actuators are two types. One is hydraulic actuator and another one is pneumatic actuator. Whenever we take hydraulic actuator, the amplification of force is very important. Whenever we take pneumatic actuator, the speed regulation is very important. In some of the mechanisms, the tool cutting mechanisms, like if you take quick return motion mechanism, the forward stroke will be almost slow, but whereas the retraction is very faster, it should come back within a short span of time. It should come back at quick. That's why the name quick return motion mechanism, because during the retrieval, during the retraction of that process, we don't have any cutting process there. So only the tool retraction, hence we can retract the back. Whereas in forward stroke, there is a cutting operation taking place. Because of that, we need to maintain the slow movement. So this is how the actuator works. There are several actuators: rotary actuator, linear actuator. So what we are taking is, we are taking an hydraulic actuator, linear hydraulic actuator, it is a cylinder. Sir, can I take rotary actuator? Yes, you can take. You can take any of the actuator, but you have to model it. Let us see how to model hydraulic actuator. Here what I have taken is, I have taken a double acting cylinder. Double acting cylinder is lifting some load. So this is a piston, this is a cylinder. And there is a displacement of the load at a displacement y, and again there is a displacement of pressure at x. So basically what we are correlating is, we are using a Pascal's law, x1 by x2. We are calculating what is the lift across the system. So let us see how to model this. So here there is a mass. I will take that as a load itself. Load is having some mass m, and the displacement of the load is y. Y I have taken, y is the displacement. You can take anything, x1, x2, that is also possible. And during retraction of this cylinder, we have a cushions. This is cushion. This cushion will be retracting the cylinder in a smooth fashion because of damping provided in between them. So there is some amount of damping. See, there is a damping, and there is no spring. If we have a spring, there is no control over hydraulic force. That's why we are eliminating spring here. After that, again, according to Newton's second law of motion, summation of forces is equal to ma, and we have written the equation for this. My double dot plus cy dot will be equal to P into A. What is this P into A? It is a hydraulic force, F. Hydraulic force F. So what is F here? Pressure is equal to force by area. What is force? Pressure into area. The same equation I have written here. This I will call it as equation A. This is a general equation for hydraulics and pneumatics. Whereas in hydraulics there is no spring here. If you consider pneumatics, we can add a plunger. That plunger movement is nothing but spring, because of which we will get a moderate speed regulation and the system will be somewhat faster. If I consider the small displacement value of x, that means if I apply some force F here, it will move at a distance of x. say F1, X1, F2, X2, same principle. If I apply some force, it will make a move of displacement X. The same thing, if I take that into a consideration, I will be introducing the values of constant K1 and K2. K1 and K2 are proportionality constants, and the value of pressure will be X minus Q. How much it is displaced minus total discharge. What is that Q? Q will be equal to A into V, area, velocity is dH by dt. So here it is dy by dt, since y is taken as a displacement here. So I will replace this. If I replace that, what happens? What will be the P? P will be equal to M divided by A and C divided by A. Sometimes it can be given as B also. C divided by A, this is the equation, plus K1 into X minus A into dy by dt. What I will do is apply Laplace transformation. If I apply Laplace transformation, K2 M by A, it will be S square Y of S plus Cs into Y of S will be equal to K1 into X1 of S plus A S into Y of S. Sorry, this is minus. I will be rearranging the term here. If I rearrange the term, what happens? The K1 will go like that. Y terms will be remains in one side. X term will be remain on other side. So directly K2 into M by A S square Y of S plus Cs by A Y of S plus this term plus A into S Y of S will be equal to only K1 into X of S. So I can take out A as a common here. K2 by A M S square plus Cs, again Y of S common here, plus As into Y of S will be equal to K1 into X of S. I have to write an expression with respect to X and Y. So what I will do is, I will be simplifying this. If I simplify this, what happens? I will take Y of S as a common, Y of S common factor, multiply K2 here. So K2 into M by A S square plus K2 into M by A S plus this term A into S into Y of S already I have taken common will be equal to K1 into X of S. Here what is the output? What is the input? The output is Y of S and input is X1 of S or X of S. So if you take this ratio, what happens? K1 divided by this term K2 ms square plus K2 ms plus A into S. So K2 C into S into A into S. So you can shift A to the numerator or you can keep as it is. So this is a transfer function for a leverage system in hydraulics. This is a ratio of displacements. If they ask ratio of displacements, you write this. This is ratio of displacements. But this is the general equation. Most of the times you can stop here itself and you can define what is the pressure. Pressure in hydraulics will be more compared to pressure in pneumatics. And this is the amplification value what we have got. Displacement amplification ratio. So this is not so much important, but if the derivation is asked for 10 marks, you have to write up to here. And here, this equation is also important. Just it is pressure will be equal to displacement minus Q. How much? Flow rate. So this is the equation. Again, it is the same thing. If you write what is the value of Q, what is the value of Q? Pressure into stroke, total pressure minus stroke length. It is just like a differential pressure equation. This is just like a differential pressure. Retraction time. This is a extension type. So this is about the derivation of hydraulic actuators. Next, let us go to pneumatic actuators. Pneumatic actuators, again the same thing. Here we are using a plunger with a pneumatic actuation. This is a diaphragm or bellows, anything you can use. And this is a pressure, pneumatic pressure what we are giving, air pressure we are giving. So pressure is the input, displacement is the output. If I write a free body diagram, it will look like this. This is a mass which is to be lifted or which is to be extended or retracted. It is just like a balloon, just compressing air and retracting air. And Ky, there is a spring here for the plunger in order to get a smooth movement. It is just like a shock absorber. And a damping is given in order to restore this, or sometimes what we will be using is we will control the speed of the actuator or plunger. For that also we need some of the damping, and we need to reduce the distortion between plunger and cylinder, piston and cylinder. We will be using cushioning. Cushioning will be given. That cushioning is nothing but damping. So if I apply Newton's second law of motion, what happens? If I apply Newton's second law of motion, again summation of forces will be equal to mass into acceleration. Here mass is m, y double dot, this is acceleration, and this is a force. What is the force across pneumatics? It is Pa minus pressure into area minus Cy dot, because it is acting away from the displacement. Displacement direction is this. These two are acting opposite to the displacement, restoring forces, minus K into Y. So rearrange this. So My double dot plus Cy dot plus Ky will be equal to pressure into area. This is a governing differential equation for pneumatic actuator. Apply Laplace transformation. It will be ms square plus cs plus k. At this point of the time, we can go faster here because you know how this ms square into y of s, cy into y of s, cs into y of s, k into y of s. So I will take y of s as a common, ms square plus cs plus k. That is the equation we will got, into y of s is equal to p of s into area. Pressure is the input, it is a variable. That's why it is P of S. So if I rearrange, output is the displacement, input is the pressure. It will be equal to what happens? A divided by ms square plus cs plus k. This is a transfer function for pneumatic actuator. This is a transfer function for pneumatic actuator. The same way you can derive the hydraulic actuator, only there is no spring. That is also possible, but the hydraulic importance is not only deriving the force expression, but displacement. The ratio of displacement is also very important here. Why? Why ratio of displacement is very important? Screw jack. The answer for that is screw jack. It will be lifting heavy load with a small stroke. What is that small stroke? That small stroke is displacement. We need to deduce an expression for ratios of displacement, x1 by x2. That is Pascal's law. Pascal's law, volume will be same. V1 is equal to V2, A1 x1 is equal to A2 x2. What is x1 by x2? A2 by A1. So like that, that ratio of displacement is very important. Here we will go in the reverse fashion. First we will be designing the displacement, then we will be going for how much it has to be lifted. So that's why in hydraulics, the optimization of hydraulics is the displacements. That's why we have deduced an equation for displacements, whereas in pneumatic it is a pressure. Because we need faster retraction, we need fast, we need slow. These things will be decided in pneumatics. Hydraulics, we want to lift heavy loads. So those two things are the major things in case of hydraulic and pneumatic actuators. So module 2, we started with mechanical systems. In the mechanical systems, translation and rotation. Wherever there is a translation, you have to use Newton's second law of motion. Even in rotation, yes, Newton's second law of motion. In translation, equation for force. In rotation, equation for torque. After that, electrical systems. Electrical systems, we have solved 4 problems. Electrical systems, we will be using KVL. Then after that, electromechanical systems, combination of electrical and mechanical systems. In that we will be using KVL as well as force voltage analogy. So that means analogous systems we have used. We are transforming mechanical system to the electrical system to the mechanical system. If you represent mechanical system as an electrical system, it is an equivalent electrical network, it is an analogy, electrical analogy. If you represent electrical system with a mechanology, it is an inverse analogy, ulta. So those things we have learned. After that, liquid level systems, tanks, that we have learned, tanks in one below the other, one after the other. So same head, differential pressure you have to take, the same different heads, directly you can deduce the equation. After that, thermal systems we have solved. Thermal systems, it is very easy, temperature and heat furnace system, then hydraulic and pneumatic actuators. So with this, we completed half of the module 2. Second part is there, block diagram reduction and signal flow graph. Mathematical modeling has been completed. Thank you.